So today we're going to begin this unit on probability. And anytime we start a new thing, it's valuable that we sort of take a moment to pause and take stock of where we are and how ready we are for this. So first, I encourage you to take a deep breath. And some of you may love probability. Some of you may have seen very little of it. Some of you may have seen a lot of it, but I hope that you'll still go through this video with me because I do want to cover some basics to probability to make sure that we have a strong foundation to build on. So in the course of this video, these are sort of the 5 things that I'm going to do. I want to talk about what is probability. I want to talk about some vocabulary and how to use it, some notation so that we know that we're using proper mathematical language, talk about experimental versus theoretical probability, and then talk about the value of counting and organizing your thoughts as we work through probability problems. Some students are led to believe that probability is really just a bunch of formulas, and honestly, probability is a lot of sort of thinking and organizing those thoughts in order to come up with these probabilities. So let's go ahead and get started. So first things first, what is probability? Well, probability is effectively the branch of mathematics, and I want to underline the word branch because mathematics has a lot of different branches. There's a lot of different directions that it goes. So probability is one of those branches of mathematics, and it explores how likely events are to occur. So there's this idea that there's uncertainty in the world, and we'd like to know how likely it is that something's going to occur. And so, we've got a couple of definitions and limitations on this. So the probability of an event occurring is always defined to be some number between 0 and 1. In other words, probabilities can never be negative, and probabilities will never be larger than 1. Okay? And the closer a probability is to 0, the less likely it is to occur. And the closer a probability is to 1, the more likely it is to occur. Okay? So if an event is impossible to occur, so if it literally cannot happen, what would we say that its probability is? Well, we would say that it has a probability of 0. And if an event is certain, that we are absolutely certain that it'll occur, we would say that it has a probability of 1. Okay? So I think that there's sort of value in the idea of sort of thinking about probability as like a continuum between 0 and 1. And the more likely something is, the closer it winds up to being 1. And the more unlikely it is, the closer it winds up being to 0. That's kind of the idea behind probability. So now I'd like to kind of take that number line idea and extend it a little bit. Or maybe not extend it, but just do an example with it, right? So I'd like you, for this problem, to consider a number line between 0 and 1. And I want you to arrange the following events along this number line corresponding to their probability. Now, please don't get out like a ruler on your screen and like make this is a thought exercise on where these events would be. So take a moment, pause the video, try these out, and sort of get a sense for what you think these probabilities ought to be. So the first one is one that you could even do numerically, right? We all have this intuitive sense that a fair coin landing tail side up when flipped should be 1 out of 2. That should be right in the middle. So right in the middle of this continuum, we're going to put A. Okay. For B, the weather in San Diego is rainy on August 5th. That's the summer. Like occasionally summer storms, but no. So this is probably going to be quite close to 0. Did I put it close enough to 0? Maybe not, probably not. What we're looking for here is the idea that things that have a low probability are closer to 0, things that have a high probability are closer to 1. Event C, the probability that at least one student is absent from your first period class on the first day of school. Again, that's not guaranteed, but we expect that to be quite high. Okay. And finally, D, that you are going through a YouTube video on probability right now. Now, as soon as I say that it should be certain and that it's going to be all the way down here at the end, in theory, somebody could be filling out this set of guided notes and not watching the video right now. But I think the majority of you are probably doing these notes as you're watching this YouTube video. And so, D is going to be, right there at the end. Very, 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 very close to 1 because it's very close to that something that's certain. So there is this idea that even if we don't have numbers associated with probability, larger numbers mean something's more likely to happen, smaller numbers means that something is less likely to happen. So next we come to the topic of vocabulary. Vocabulary is really, really, really valuable in mathematics. We pride ourselves on being very, very precise and making sure that we all know what we're talking about in these things. Vocabulary is especially important for you as IB students because at some point you're going to need to write an IA, your internal assessment. And when you write that, using proper vocabulary, using those words properly is really, really valuable. So I've sort of got these 4 vocabulary words that I want to make sure that we're all comfortable with before we go on. So first is the idea of a trial. In probability, the word trial refers to a thing that happens that we can track the outcomes of. Okay, so rolling a die can be a trial. Determining what the weather is on a given day can be a trial. Finding out what the temperature inside of your refrigerator from hour to hour could be a trial. Any sort of experiment or thing that you can do and track the outcomes of is a trial. Okay? Next is an event. Okay? An event in probability is a specific outcome of a trial. Okay, so I think one of the most important distinctions here is between trial and event. Lots of times somebody will say, oh yeah, I have an event. An event is I roll a 6-sided die. And that's not an event though, that's a trial. An event would be you roll a 6-sided die and get a 4. Or you roll a 6-sided die and get an odd number. So that's the difference between trial and event. Okay. Next is the complement of an event. Now, the complement of some event is just the opposite of that thing. So if your event was rolling a 4, the complement would be rolling not a 4. If your event was rolling an odd number, then your complement would be rolling an even number. Okay. And finally, sample space. Sample space is going to be a really, really important one. We're going to use it actually all of these are important. We're going to use all of them throughout probability. Sample space is just the listing of every possible outcome of a trial or an experiment. Now, I kind of want to do a bit of like just a mini example of us using this information, right? So let's say that we conducted a trial. Right? Our trial is that we want to roll 2 4-sided dice and add up the results. So this is a trial because it's a thing that happens. It's a thing that we do that we can track the outcomes of. Okay? Now, let's think about what an event for this would be. Right? An event for this might be that we roll 2 4-sided dice and we add up the results, and the event part is that the sum is odd. Okay? And of course, the complement of that event that we just mentioned is that rolling those 2 6-sided dice, rolling those 2 4-sided dice and the sum being even instead of the sum being odd. And finally, the sample space. So the sample space is where we list all of the possible outcomes of a trial. And sometimes the only way that we can sort of see that is to come up with some sort of a diagram. So if we sort of imagined here that we built a little chart where we were going to write down all of the 1, 2, 3, 4 on one die, 1, 2, 3, 4 on the other die, and then added them up. My goal right now is not to get into the probability of this, but just to look at the sample space. If we built a little chart of what these sums would be, we can tell that the sample space is effectively numbers between 2 and 8. So my sample space would be the set 2, 3, 4, 5, 6, 7, 8. And those weird things I put at the end are just like curly brackets or curly braces. So this is the vocabulary that we're going to need to get through, particularly to get through this lesson, but also to get through the next few lessons. Now, hand in hand with vocabulary is notation. So vocabulary are effectively the words that we use. Notation are effectively the symbols that we use for this. And so a couple notes about notation. Notes about notation. Events are generally denoted using capital letters, and it's good form to indicate both the event and the trial in these definitions. Okay, so I gave you 2 little examples here, right? So the first one is this idea that the A could be the event that when a fair 6-sided die is rolled, there's your trial, the result is odd. That's the part that makes it an event. Okay, another example here, let B, again, capital letter B, let B be the event that it rains on any day in the month of August in San Diego. So the trial here is probably, the weather on a given day in August in San Diego. And the event is that it rains. Okay. Another comment about notation: for the complement of an event, we generally denote that with a little prime, this little sort of apostrophe up here. So if the original event is A, then the complement would be A prime. And because they're sort of opposite events, if I add together the probability of it happening or not happening, that probability is going to be 1. That's something that's called the law of the excluded middle. So just you don't need to know that, but it's a point for you to know. And the final thing, and this is a notation I kind of just used up here, the probability of an event A occurring is always denoted this way, capital P of A. Okay, so if someone were to write P of B, This means the probability of the event B happening. Sometimes you'll see that people will do something like the probability of rolling an odd number on a die. This is also common. It's not uncommon to see people just write a sentence in there where they describe the event. But I think when we're working with formulas and things, we're generally going to go for a notation that's a little bit more like that. So we've just got a few more background things to get through before we're going to get to some sort of examples of these things. When we start a new subject, there's often a lot of sort of background information that we need to pick up. So the next of these things is this idea of experimental versus theoretical probability. Now, I don't want to spend a lot of time here, but the idea is that there are two different ways that we can sort of think about probability. And one of them is experimental probability, and the other is theoretical probability. Neither of them is really better than the other. They're really just different approaches to determining the likelihood of an event. I suppose in general we could say that experimental probability gets us an approximation of what the true probability is, and theoretical probability sort of gets us this, well, theoretical or perfect expression of what the likelihood of an event is. There are formulas for experimental and theoretical probability. I'm going to explain them really, really briefly here. The idea in experimental probability is that you probably did that by carrying out an experiment. You did some large number of trials, and the experimental probability is just on the denominator, the number of times the event A could have occurred. In other words, the number of times you carried out your trial. And in the numerator, the number of times that trial ended up happening that A happened. So experimental probability is really just how many times does A happen, does the event happen, divided by how many times did you try and have the event happen. Okay. Now in theoretical probability, we're not carrying out experiments. We are thinking theoretically about the sample space. We're thinking about how many ways could this thing have happened, and then out of all of those, how many ways did event A happen? So for theoretical probability, in the denominator, you're going to put down how many things are there in the sample space, how many different outcomes were possible, and in the numerator, how many of those outcomes had event A happening. I mean, both of these things are very, very similar in terms of how they're carried out, and that's the difference between experimental and theoretical probability. I've now got a really quick example of seeing the difference between theoretical and experimental probabilities. So go ahead and pause the video for a moment and carry out this example for yourself. All right, so for question A, what is the experimental probability of obtaining an odd result? Well, we said that the die was thrown 1,000 times. That means we did the trial 1,000 times. And then in the numerator, we just need, how many times did it turn out odd? That would be 117 plus 131 plus 140 plus 128. And the work I did over here in my side work is that was 516. So the experimental probability of obtaining an odd result for this example was 516 out of 1,000. Question B, what is the theoretical probability of obtaining an odd result? Well, in this case, a fair 8-sided die is thrown. We can see that the results are 1, 2, 3, 4, 5, 6, 7, and 8. There are 8 different things that are in the sample space. 4 of those things are odd, and so we wind up getting that the theoretical probability of getting an odd result is 4 out of 8, or 1/2. I could also simplify the top one. Simplification isn't absolutely necessary. I kind of want us to get a sense of the difference between the experimental and the theoretical probabilities. To be fair, the majority of the work that we're going to be doing in the rest of this unit is on theoretical probabilities. Experimental probability, I'm sure that there's a lot more complex stuff to be said about it, but as far as the IB exam is concerned, you really just need to know that you're sort of counting the number of trials on the bottom and how many trials turn out favorably on the top. Theoretical probability, figuring this out through thought, there's a lot more complexity, and so we need a lot more tools to work with that. So that's why we're going to spend more time learning about that. So I have 3 examples left in this video, and in the final part of the video, I really want to talk about the value of counting and organizing your thoughts. At some point, we are going to develop some advanced formulas for probability, but very often probability comes down to counting, diagrams, and sort of thinking through the likelihood of these events. And so let's go ahead and go right into this next example. A fair coin is flipped 3 times. Make a list of the sample space of outcomes, and then use it to determine the probability that exactly 2 of the coins come up tails. So what we really need to be doing here is we need to be coming up with that sample space of outcomes. And it's really important when you make the sample space, you can't just say, well, there could be 0 tails, there could be 1 tails, there could be 2 tails, there could be 3 tails. That's a list of just the totals. It's not really a list of the outcomes. Okay? When I flipped this coin, there was a first coin, there was a second coin, there was a third coin. And so what we're going to want to do here is we're going to sort of want to make a little table here where we document what were the results of the first, second, and third coins. Now, there are some methods that you can use to sort of document this more carefully, and I'm going to try and show you one of them here now. So what we do here is the idea that we say, let's figure out all the ways that we could get heads first. Well, we could get heads on the first coin, and then heads on the second coin, and then heads on the third coin. We could also have gotten heads on the first 2 coins and tails on the second coin. Okay. At this point, we've sort of exhausted all the ways that we can get heads on both of the first 2 coins because we've gotten all of these results. So then I keep heads here, but now I let the second one be tails. And I go to this being heads, and then we do heads and tails, tails. And at this point, I've sort of used up all of the ways that the first coin can be heads. So now I'm going to do sort of the same thing, but now I want to look at what are all the ways that the first die could have been tails. Not the die, the first coin could have been tails. So we'd have tails and heads and heads, and tails and heads and tails. I've now used up all the ways that the first one can be tails and the second one can be heads. So now the second one gets a chance to be tails. Tails, tails, tails. At this point, we've gone through all of the different ways that these 3 coins can be flipped. And now we can find the theoretical probability of exactly 2 of them coming up tails. Okay? We can tell that there are 8 things in the sample space. There are 8 ways that this trial could have gone. And where are the ways that we ended up with 2 tails? Let's see here. There's one of them here. There's one of them here. And there's one of them here. So there are 3 total ways out of the 8 trials that we can wind up with exactly 2 tails. So hope you can see through this example that counting and organizing your work are going to be really, really important as we work through probability. So if you aren't really good at organizing your work, let's use probability as a unit where we practice that and we work on that skill. Organization is definitely something that we can grow in over time. People are not organized or not organized. There's opportunity for you guys to grow in this, so give yourself a chance. So here I have another example where we're going to be counting and we're going to be organizing our thoughts. So a fair 6-sided die and a fair 4-sided die are thrown, and the results of the rolls are multiplied. I want us to construct a lattice diagram or a grid for the situation, and then use it to determine the probability that the product of the 2 dice will be a prime number. So you may already know what this means. If so, pause the video and do it on your own. If you're not sure what a lattice diagram or a grid is, it's something that we saw earlier in the video, actually. The idea is you can just make a big chart where you write down all the things that could happen. Right? Our 4-sided die would be 1, 2, 3, 4. Our 6-sided die would be 1, 2, 3, 4, 5, 6. And then you fill in the chart according to what they asked for. In this case, they said find the product of the numbers. They could have said add the numbers. They could have said subtract the numbers. They could have said find the greatest common factor. They could have, there's any number of things that it could be. In this one, we're supposed to be doing a product. So at this point, pause the video, fill out the lattice diagram, and then answer the question. All right, so here I have my completed lattice diagram, and I can see all of the things that are possible. I'm effectively looking here at the sample space, okay? So the next thing that I need to do is I need to go through and identify, okay, so which of these numbers are prime? Okay, well, 2 is prime, and 3 is prime. 2 is prime, 3 is prime, 5 is prime. 1 is not a prime number, just in case anybody was wondering about that. The definition of a prime number is a number that has exactly 2 prime factors, and 1 only has 1 prime factor. The rest of these numbers are all composite. They're all things that have 2 things multiplied together, that aren't them in 1. So as far as I can tell here, there are 5 prime numbers out of my total of 24 things in the sample space. So my theoretical probability that the product is a prime number is 5 out of 24. In the final example, I want to remind you guys or let you know sometimes counting all the ways something can happen is going to take too long or it can be cumbersome. And it can be helpful to remember that we have this thing called the complement. right? Instead of looking at the probability of something happening, we can think about the probability of it not happening and then subtract that from 1. Okay? So for this example, I want you to think about rolling 2 fair 12-sided dice and adding the results together. And you're being asked here to find the probability that the sum of the 2 dice is greater than 4. So think for a moment what a lattice diagram for this problem would look like. If you need to, pause the video. So, a lattice diagram for this problem would effectively look like a giant table where I would have the numbers going 1, 2, 3, 4, 5, 6, all the way down to 12. And up here I would have 1, 2, 3, 4, 5, all the way over to 12. There would be 144 things in this table. I don't want to have to write all 144 of those things out, but you'll notice I already put that in the denominator, because that's how probability works, right? I'm supposed to put the number of things in my sample space in the denominator, and in the numerator, I'm just putting down how many of the things fit that qualifier that I'm looking for. Now, the question is asking, how many places is this sum greater than 4? That's a lot of things. So maybe instead what I should do is look for the things where it's not greater than 4. Way up here in this corner of the lattice diagram, I'd have 2, 3, 4, 5. I'd have 3, 4, 5. I would have 4, 5, 6. Like, you can sort of like see what the top of this chart would look like, right? What I'm looking at, the problem says find the probability that the sum of the 2 dice is greater than 4. So that would be like all of this stuff. Okay? It's a lot easier for me to just look at this and say, well, if you take a look up here, there are 1, 2, 3, 4, 5, 6. There are 6 things out of 144 that are 4 or less. And so if we want the probability that it's greater than 4, we just need to do 1 minus this. That would give me 138 out of 144. I know we're at the end of a long video, but I hope that one made sense. If you need to, pause the video, go back and look at that one again. This strategy of using the complement and thinking about the opposite of the event that you're looking for is really, really, really valuable in helping you to not have to count giant lists of numbers. I hope all that made sense. I'm really looking forward to going through more probability with you guys in the days and weeks to come. And I hope that you'll keep an open mind on it and use this as an opportunity to grow in, organizing and all of those sorts of things. So best of luck.